Welcome! In today's session, we'll be solving LeetCode problem number 88, Merge Sorted Array. This is a classic problem that tests your ability to work with arrays and sorting techniques. We'll explore different approaches to solve this problem, analyze their efficiency, and understand when to use each one. Let's dive in. In this problem, you are tasked with merging two sorted integer arrays, nums1 and nums2, into a single sorted array. Both arrays are given to you in non-decreasing order, and you are also provided with two integers, m and n. These integers represent the number of initialized elements in nums1 and nums2, respectively. The key point here is that the merged result should not be returned as a new array. Instead, the merged and sorted elements must be stored directly in nums1. To accommodate this, nums1 has extra space at the end, represented by zeros, which should be ignored during the merging process. Specifically, the first m elements of nums1 contain the initialized values to be merged, while the last n elements are placeholders. On the other hand, nums2 contains exactly n sorted elements. Your task is to modify nums1 in place so that it contains all elements from both arrays, sorted in non-decreasing order. Let's take a look at an example to understand this better. Suppose nums1 is 1, 2, 3, 0, 0, 0, and nums2 is 2, 5, 6, with m and n both equal to 3. Initially, the first three elements of nums1 are 1, 2, 3, which are sorted, and nums2 contains 2, 5, 6. The goal is to merge these two arrays such that the result is sorted and stored in nums1. After merging, nums1 becomes 1, 2, 2, 3, 5, 6. Notice how the zeros in nums1 were replaced with the elements from nums2 in the correct order, ensuring the entire array remains sorted. This demonstrates how the merging process works while modifying nums1 in place. Now, consider another example. Here, nums1 is 1, nums2 is an empty array, and m is 1 while n is 0. Since nums2 is empty, there are no additional elements to merge into nums1. As a result, nums1 remains unchanged, and the final array is simply 1. This highlights an important edge case where one of the arrays is empty. When nums2 contains no elements, nums1 remains as it is, provided its initialized elements are already sorted. In the next example, we have nums1 as 0, nums2 as 1, m equal to 0, and n equal to 1. Here, nums1 has no initialized elements, meaning the merging process involves copying all elements from nums2 into nums1. After the merge, the result is 1, which is stored in nums1. This illustrates another edge case where nums1 starts with no meaningful values, and all elements from nums2 are directly transferred into it. Finally, keep in mind a few important constraints and edge cases. The total length of nums1 is always m plus n, and nums2 has exactly n elements. The number of initialized elements, m and n, can range from 0 to 200, and the values within the arrays can be as small as -10 to the power of 9 or as large as 10 to the power of 9. Both arrays are guaranteed to be sorted in non-decreasing order, and the merging process must preserve duplicates. Additionally, there may be cases where elements from nums2 need to be interleaved between those in nums1, requiring careful comparison at each step. By handling these scenarios correctly, you can ensure the merged result is always accurate and sorted in place. To begin, let's consider the brute force approach. The intuition here is quite simple. We take all the elements of nums2 and append them to the extra space already available in nums1. Once all the elements are in one place, we can use a built-in sorting algorithm to reorder nums1 in non-decreasing order. This method is straightforward and leverages the power of sorting functions. However, the time complexity is m plus n, log m plus n, because of the sorting step, and even though it operates in place without additional memory, it's inefficient. The arrays are already partially sorted, so sorting the entire array again introduces unnecessary overhead. While this approach is easy to implement, it isn't optimal when compared to more sophisticated strategies. Next, we consider an improved method using two pointers, starting from the front. The idea here is to use one pointer for nums1 and another for nums2, allowing us to traverse both arrays simultaneously. As we compare the elements at the pointers, we add the smaller of the two to a new result array. Once the traversal is complete, we copy the merged and sorted result back into nums1. This approach significantly improves the time complexity to O, m plus n, as it only requires a single pass through both arrays. However, it introduces extra space complexity of O, m plus n, because of the new result array. While this method is more efficient in terms of time, it doesn't meet the problem's requirement for in-place merging, making it less ideal. Now we arrive at the optimized approach, 2 pointers starting from the back. This method takes full advantage of the extra space already available in nums1. Instead of creating a new array, we work directly within nums1, filling it from the back to avoid overwriting elements. Here's how it works: we initialize 3 pointers. One, P1, points to the last valid element in nums1, another, P2, points to the last element in nums2, and a third, P, starts at the last position of nums1, where the merged result will be placed. As we traverse, we compare the elements at P1 and P2. The larger value is placed at nums1, P, and the corresponding pointer is moved backward. If any elements remain in nums2 after this process, we copy them directly into nums1. This approach achieves both O, m plus n, time complexity and O1, space complexity. While slightly more complex to implement, it is highly efficient and meets the in-place constraint. The chosen strategy is the 2 pointers approach starting from the back. This method stands out as the most efficient solution in terms of both time and space complexity. The key insight here is that by filling nums1 from the back, we avoid overwriting its existing elements while maintaining the sorted order. This eliminates the need for additional arrays or sorting steps, which are required in the other approaches. The aha moment in this strategy is recognizing that working with the largest elements first simplifies the merging process and ensures correctness without extra memory. Overall, this approach is efficient, adheres to the problem's constraints, and is relatively straightforward once the logic is understood. It strikes the perfect balance between clarity and performance, making it the ideal choice for solving this problem. To solve the problem of merging 2 sorted arrays, we need to efficiently combine the elements of nums1 and nums2 into a single sorted array. The unique challenge here is that the nums1 array already has extra space at the end to accommodate all elements from nums2. Specifically, the first m elements in nums1 are sorted, while the last n elements are placeholders filled with zeros. The nums2 array, on the other hand, contains n sorted elements. Our task is to modify nums1 in place, meaning we cannot use additional arrays to store intermediate results. The key idea is to leverage the fact that both arrays are sorted. Instead of merging from the beginning, we can use a 2-pointer approach starting from the end of both arrays. This allows us to place the largest elements directly into their correct positions in nums1, avoiding the need for additional space and ensuring the process is efficient. To implement this, we first establish 3 pointers. The pointer P1 starts at the last non-placeholder element in nums1, which is at index m1. The pointer P2 starts at the last element of nums2, which is at index n1. Finally, the pointer P begins at the very end of nums1, at index m plus n1. With these pointers set up, we can begin merging in reverse order. At each step, we compare the elements at nums1, P1, and nums2, P2. Whichever is larger gets placed at nums1, P, and the respective pointer, either P1 or P2, is decrement. After placing an element, the pointer P is also decrement to move to the next position. If nums2 still has elements left after this process, we copy them directly into nums1. On the other hand, if nums1 has remaining elements, no action is needed since they are already in place. This approach also naturally handles edge cases. For example, if nums2 is empty, nums1 remains unchanged because it's already sorted. If nums1 contains only placeholders, we simply copy all elements from nums2. Duplicate elements are handled seamlessly as well, thanks to the stable nature of the comparisons. The choice to merge in reverse order is critical for this algorithm's success. By placing elements at the end of nums1, we avoid overwriting any of its valid elements, ensuring that no data is lost during the process. This strategy leverages the extra space in nums1, making the merge conflict-free. In terms of efficiency, the algorithm is highly optimized. It processes each element from nums1 and nums2 exactly once, resulting in a time complexity of O, m plus n, where m and n represent the lengths of the 2 arrays. Additionally, since the algorithm modifies nums1 in place, no extra space is required beyond the pointers we use, making the space complexity 1. This is a significant improvement over a brute force approach that involves concatenating the arrays and sorting them, which would take m plus n, log m plus n, time and additional memory. The two-pointer method is not only faster but also more memory efficient, making it a robust solution for merging sorted arrays. In this algorithm, the key data structures are the input arrays themselves and the 3 pointers used to manage the merging process. The nums1 array serves as both the input and the final destination for the merged elements. Its extra space at the end enables us to perform all operations in place. The 3 pointers P1, P2, and P play a crucial role in ensuring efficiency. The pointer P1 tracks the current element in the valid portion of nums1, P2 tracks the current element in nums2, and P determines where the next largest element should be placed in nums1. By using these pointers, we avoid redundant work and ensure that the merging process is both fast and orderly. To illustrate the process, consider an example where nums1 equals 1, 2, 3, 0, 0, 0, with m equals 3, and nums2 equals 2, 5, 6, with n equals 3. This setup provides an opportunity to see how the pointers interact and how elements are merged step by step. Let's walk through the example step by step. Initially, the pointers are set as follows: P1 equals 2, pointing to the last valid element in nums1, P2 equals 2, pointing to the last element in nums2, and P equals 5, pointing to the last position in nums1. In the first comparison, nums1, P1, is 3, and nums2, P2, is 6. Since 6 is larger, we place it at nums1, P, then decrement P2 to 1 and P to 4. Next, we compare nums1, P1, 3, and nums2, P2, 5. Again, 5 is larger, so we place it at nums1, P, and decrement P2 to 0 and P to 3. Now, we compare nums1, P1, 3, with nums2, P2, 2. This time, 3 is larger, so it goes to nums1, P, and P1 is decrement to 1, with P moving to 2. In the next comparison, both nums1, P1, and nums2, P2, are 2. We place 2 at nums1, P, decrement P2 to -1, and P to 1. At this point, nums2 has no remaining elements, so the process is complete. The final merged array is 1, 2, 2, 3, 5, 6, which is sorted as required. This Python implementation solves the merge sorted array problem using an approach that merges the arrays in reverse order, starting from the end. Here is a detailed explanation of the code. The function merge takes 4 parameters: nums1, the first sorted array with extra space at the end, m, the number of actual elements in nums1, nums2, the second sorted array, and n, the number of elements in nums2. First, we define 3 pointers. P1 is initialized to the last valid element in nums1 at index m1. P2 is initialized to the last element in nums2 at index n1. P is the position where the next largest element should be placed in nums1, starting at the end of the array, m plus n1. The main logic is handled in a while loop that continues as long as there are elements in both nums1 and nums2, P1 equals 0 and P2 equals 0. Inside the loop, we compare the elements pointed to by P1 and P2. If nums1, P1, is greater, we place it at the position P and decrement P1. Otherwise, we place nums2, P2, at position P and decrement P2. In either case, we decrement P to move to the next position. After the main loop, if there are any remaining elements in nums2, i.e., if P2 equals 0, we copy them into nums1 using another while loop. This ensures that all elements from nums2 are correctly merged. We do not need to handle the remaining elements in nums1 explicitly because they are already in place. The algorithm modifies nums1 in place, and the final result is stored directly in nums1. This reverse merging approach is efficient, with a time complexity of m plus n, as each element is processed once. The in-place modification of nums1 ensures that the space complexity remains 1. This is the Java implementation of LeetCode problem number 88, merge sorted array. The solution mirrors the Python logic, using 3 pointers to merge 2 sorted arrays in place. Key differences include Java's use of explicit type declarations and array handling. The algorithm sorts elements starting from the end of the arrays, ensuring that no extra space is used. If elements from nums2 remain after comparison, they are directly copied into nums1. Here, we start with a basic example to understand the merging process step by step. We are given nums1 as 123000 with m equals 3, and nums2 as 256 with n equals 3. The extra zeros in nums1 provide space for merging the two arrays. To begin, we initialize 3 pointers, p1 pointing to the last element in the valid part of nums1, which is at index 2, p2 pointing to the last element in nums2, also at index 2, and p pointing to the last available position in nums1, at index 5. Now, we compare the elements at p1 and p2. Since nums2, p2, which is 6, is greater than nums1, p1, which is 3, we place 6 at nums1, p. This updates nums1 to 123006. After placing the larger element, we decrement both p2 and p by 1. In the next comparison, nums2, p2, is 5, and it's still greater than nums1, p1, so we place 5 at the next available position in nums1. The array becomes 123056, and we repeat the process. When nums1, p1, which is 3, becomes greater than nums2, p2, which is 2, we place 3 at the current position, updating nums1 to 123356. This continues until p2 becomes -1, meaning all elements of nums2 have been merged. The final merged array is 122356. Next, we examine 2 edge cases that illustrate how the algorithm handles special scenarios. In the first edge case, nums1 is 123 with m equals 3, and nums2 is an empty array with n equals 0. After initialization, we set p1 to 2, p2 to -1, and p to 2. Since p2 is already less than 0, there are no elements in nums2 to merge. This means nums1 remains unchanged as 123. The second edge case flips the scenario. Here, nums1 starts as 000 with m equals 0, meaning it's essentially empty, and nums2 is 123 with n equals 3. Because nums1 has no valid elements, all the merging will involve copying elements from nums2 into nums1. In this second edge case, the algorithm begins by initializing the pointers. p1 is set to -1 because there are no valid elements in nums1, p2 starts at 2, pointing to the last element in nums2, and p is set to 2, the last index in nums1. Since p1 is less than 0, we directly copy elements from nums2 to nums1. First, we take nums2, p2, which is 3, and place it at nums1, p, updating nums1 to 003. We then decrement both p2 and p. Next, we copy nums2, p2, which is 2, into nums1, p, resulting in 023. Finally, we copy nums2, p2, which is 1, into nums1, p, producing the final merged array, 123. The algorithm terminates once p2 becomes less than 0. These examples highlight key insights. The algorithm works in reverse to avoid overwriting elements in nums1, handles an empty nums2 by leaving nums1 unchanged, and efficiently copies elements when nums1 is initially empty. Additionally, the space complexity remains 1, as no extra arrays are used. The time complexity of this solution is determined by the number of operations required to merge the two arrays, nums1 and nums2, in place. First, we iterate through both arrays using a loop that compares elements starting from the back of the arrays. During each iteration, the larger of the current elements from nums1 or nums2 is placed in its correct position in nums1. Since every element from both arrays is processed exactly once, this loop runs at most m plus n times in the worst-case scenario. After this, there may still be elements remaining in nums2 that need to be copied into nums1. This second loop, which handles those remaining elements, runs at most n iterations. Combining both loops, the total number of operations is proportional to the sum of the sizes of the two arrays, m plus n. Therefore, the overall time complexity is m plus n. The space complexity of this solution is minimal because the algorithm modifies nums1 directly without allocating any additional data structures. To break it down, the solution only uses a constant amount of extra memory for a few pointers, p1, p2, and p. These pointers are used to track positions within the arrays during the merge process. Since no new arrays or other data structures are created, the memory usage does not increase with the size of the input. As a result, the space complexity is constant, or O1. This efficiency is a key advantage of the in-place approach used by the solution. The performance of this algorithm can be analyzed further by considering the best, average, and worst-case scenarios. In the best case, if one of the arrays is empty, the algorithm only needs to copy the other array into nums1, which still results in O, m plus n, time complexity but with fewer iterations. In the average case, when the arrays have roughly equal numbers of elements, the algorithm performs O, m plus n, comparisons and placements to merge them. In the worst case, when both arrays are fully populated, the algorithm processes every single element, resulting in O, m plus n, time complexity as well. Now, comparing this to a naive approach, where you might create a new array, combine nums1 and nums2, sort the combined array, and then copy the result back into nums1, the time complexity would increase to O, m plus n, log, m plus n, due to sorting, and the space complexity would rise to O, m plus n, for the additional array. The given solution is much more efficient because it takes advantage of the fact that the input arrays are already sorted, reducing both time and space complexity to O, m plus n, and O1, respectively. To solidify our understanding, let's mathematically prove the time and space complexity. For time complexity, the algorithm processes each element in nums1 and nums2 exactly once. If we let t, m, n represent the total runtime, it is clear that the number of operations grows linearly with the total number of elements, m plus n. Thus, the time complexity is O, m plus n. For space complexity, the algorithm only uses a fixed number of pointers, p1, p2, and p. These pointers do not scale with the size of the input, meaning the memory usage remains constant regardless of the input size. Therefore, the space complexity is O1. This combination of linear time complexity and constant space complexity makes the solution highly efficient for merging two sorted arrays. When solving the merge sorted array problem, there are a few common mistakes to watch out for. First, some solutions overlook the fact that both arrays are already sorted. Instead of leveraging this property, they merge the arrays and then sort the result, which is inefficient and increases the time complexity unnecessarily. Another frequent mistake is using extra space when the problem specifically requires in-place merging. For example, creating a new array for the result violates the constraints and isn't allowed in this problem. Edge cases are also a point of failure for many developers. Situations like nums2 being empty or nums1 containing only placeholder zeros need to be handled carefully. Additionally, overwriting the placeholder values in nums1 too early can lead to losing important data, especially if merging doesn't start from the back of the arrays. Lastly, pointer mismanagement is a big pitfall. If the pointers aren't updated correctly, it could lead to incorrect results or even infinite loops. Being mindful of how pointers move is crucial for success. Now, let's focus on what insights you should keep in mind during an interview. The merge sorted array problem is a variation of merging two sorted lists, so recognizing the pattern and applying a two-pointer approach is key. The optimal solution involves merging from the end of both arrays, which prevents overwriting values in nums1 and ensures an efficient O, m plus n, time complexity. It's also important to be prepared to discuss edge cases, such as how your solution handles empty arrays or duplicates, as interviewers often test for robustness in these scenarios. Additionally, you might encounter follow-up questions where you'll need to adapt the solution for larger datasets, like arrays stored in external memory. Another way to prepare is by exploring related problems. For instance, LeetCode 21 involves merging two sorted linked lists, which share similar logic. Other problems like LeetCode 148 and LeetCode 23 challenge you to merge or sort lists in more complex scenarios, further building on the concepts used here. Considering alternative approaches can also enhance your understanding of the problem. The two-pointer approach is the optimal method. By merging from the back of the arrays, you avoid overwriting values in nums1 and achieve efficient O, m plus n, time complexity with constant space. However, it does require careful pointer management to ensure correctness. A simpler, though less efficient, approach is the brute force method, where you append nums2 to nums1 and sort the result. While this has a higher time complexity of O, m plus n, log, m plus n, and may work for smaller datasets, it's not suitable for larger inputs. Another alternative is to merge into a new array first and then copy the result back into nums1. This method has a time complexity of O, m plus n, but it uses extra space and violates in-place requirements, making it less ideal for this particular problem. Understanding these trade-offs helps you choose the best approach based on the constraints and context. Great job! We've successfully solved the merge sorted array problem and reviewed its key concepts. Remember, mastering such problems is all about practice and understanding the trade-offs between approaches. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!